The human body operates as a massive coordination chemistry laboratory. To understand its complexity, we have to look past the macroscopic biological systems and focus on the microscopic interactions occurring at the molecular level. Within this laboratory, large proteins serve as multidentate ligands. They wrap around central metal ions, which act as the geometric and electronic anchors for the chemical reactions that sustain life. Analyzing these systems requires a shift in focus. By prioritizing the electronic properties of the central metal rather than the massive protein scaffold, the logic behind complex biological enzymes becomes clear. Textbooks often present this field as an overwhelming list of metalloproteins. Looking at these information overload tables, it feels like every enzyme requires individual memorization of its specific metal and function. However, most roles are dictated by the metal's d electron count. Take zinc 2+. Because it possesses a completely filled d10 configuration, it lacks the empty orbitals required for electron transfer. This precludes it from performing redox chemistry, restricting its biological role to structural support, or acting as a Lewis acid in hydrolysis. We see similar logic with other elements. Sodium and potassium are S-block ions with single, stable oxidation states, making them the primary tools for maintaining ionic gradients and charge transport. In contrast, transition metals like iron and copper can toggle between multiple oxidation states, such as iron 2 and iron 3, which is the specific requirement for oxygen transport and catalytic redox reactions. When you identify these fundamental inorganic properties, the biological function of the system becomes a predictable outcome of the metal's position on the periodic table. Hemoglobin provides a clear example of this inorganic logic. This diagram shows the structural relationship between the iron center and the surrounding porphyrin ring, which is the key to how oxygen binding triggers a conformational change in the entire protein. In the deoxy state, the iron 2 center is in a high-spin electronic configuration. The occupation of the antibonding orbitals increases the metal's atomic radius to the point where it cannot fit into the porphyrin plane. It sits roughly 0.7 angstroms below the ring, pulling on the attached histidine residue. When an oxygen molecule binds to the vacant coordination site, it acts as a strong field ligand, significantly increasing the crystal field splitting energy. This electronic shift forces the d electrons to pair, transitioning the iron to a low-spin state. As the antibonding orbitals are vacated, the radius of the iron contracts. The smaller ion snaps into the plane of the porphyrin ring, physically dragging the histidine residue upward. This single atomic movement is what initiates the cooperative binding effect. The macroscale process of human respiration is effectively driven by this microscopic transition in electron spin pairing. This relationship is frequently tested using a specific scenario. Why can't we use naked heme groups for oxygen transport? This exam question asks why isolated iron 2 porphyrins fail to transport oxygen reversibly in an aqueous environment. Without the surrounding protein chain to provide steric hindrance, 2 iron porphyrin complexes would collide and react with oxygen to form a stable mu-oxodimer. This process is irreversible, effectively locking the iron in an oxidized state and preventing further oxygen transport. Beyond hemoglobin, you must be able to differentiate the 3 primary macrocyclic rings used in biological coordination. While heme uses a symmetric porphyrin ring, vitamin B12 utilizes a corin ring. It coordinates a central cobalt atom, but the ring itself is less symmetric because it lacks one of the methane bridges found in porphyrins, resulting in a more contracted coordination environment. In the structure of chlorophyll, the central metal is magnesium. It is coordinated by a chlorin ring, which is a porphyrin derivative where one of the double bonds in a pyrrole ring has been reduced. While the central metal determines the core chemical potential, these variations in the organic ring system refine the enzyme's geometry for specific biological targets. This matching question from a previous competitive exam looks complex because of the multiple columns. However, we can solve it by applying the periodic trends we've already identified. By connecting zinc to carbonic anhydrase based on its requirement for a non-redox Lewis acid, we can immediately eliminate 3 of the 4 multiple choice options. The complex biological names become secondary to the underlying inorganic requirements. To summarize, iron and copper facilitate redox and oxygen transport. Porphyrin, corin, and chlorine rings are distinguished by their symmetry and saturation. Zinc is the primary anchor for hydrolysis, and the transition from high-spin to low-spin iron is the mechanical trigger for hemoglobin's function. By analyzing biological systems through the lens of transition metal chemistry, the complexity of the protein is removed, leaving a system governed by the fundamental rules of the periodic table.